Hey everyone. Thanks for coming to my talk. Yeah, the talk is called Database Compiler in XTDB. I'm going to talk a bit sort of about the differences and the similarities between compilers and databases, and in the context of XTDB. So the thing you're probably thinking, okay, what is he talking about? I'm using a database and a compiler every day, and they do quite different things for me. And so yeah, so that's why I want to start with the first question: where are they the same? And then afterwards, we might gonna have a look at where they actually differ and how they differ. Yeah. So where are they the same? For that, I'm going to talk about intermediate representations. So in compilers, you have this concept of intermediate representations. Let's think about your closure file. So that gets compiled to Java bytecode, and then that gets executed by the JVM as machine instructions, and sort of the bytecode is an intermediate representation. Okay, and in XT we kind of have something very similar. Yeah, so we have SQL and Datalog. We support that kind of as top-level languages. And then, I'm sorry, I'm going to take this out, otherwise it's going to be awful. Yeah, and then we have like these intermediate representations, we call them logical plans. And in this diagram, you see 3 of them, and then in the end, we execute this logical plan to get results, get the results back. These intermediate representations, in our case, are in relational algebra, which is kind of the SQL of the academic world. And what's so nice about relational algebra, like there's been 50 years of research on that, so you can essentially tap in. I think John mentioned that in his XTDB talk as well, in all kinds of research. So you can just go off, read some paper. Hey, there's a new operator. Let's implement that, and let's see how it performs. And yeah, so that's something that's nice about this. The other thing that is really nice is that any optimizations you do in the middle, they kind of carry over to both query language that we support. So I'm just gonna give you an example of what this might look like. Here is a query in Datalog. We just have, we query for a bunch of users. So we have this new match syntax, which essentially says, please get me some user, or like walk over the user table, and then we have like the name column or the name attribute, bind that to the username, and then project that out. And so this is what then the RI, the relational algebra, will look like. It's kind of straightforward. It's represented still in as closure data structures with sort of nested vectors. So we have like a scan the table of users, get the name column, and then on top of that do the renaming in the project from name to username. Yeah, so I've brought this example to kind of give you an idea of some optimization we do in the intermediate representations. So we have an SQL statement which has like an outer query and inner query. We have some orders. So orders could have multiple items associated with it that get shipped. And in this query, essentially, we want to know, hey, for which orders there was like a shipping that was late. So that's sort of the commit date. We committed to some arrival date, and then the receipt date was after that. And here in the sort of inner query, we also referenced the outer orders table. So this is what is called a correlated subquery. So this subquery references the orders table above. Yeah. So now that's what it's going to look like. No, let's go back. I forgot something. When you think about how you might want to execute this, you could say, okay, what's the most naive thing we can do? let's walk the orders table, and then for every order, we want to do like check the shipping table. Hey, when something matches and like the commit date is before my receipt date, we get that out. The problem with that is that, let's say the two tables are of order of magnitude like n, then that is a nested loop, so you get like n squared complexity. But that's what we first actually do when we create the intermediate representation. We just do this naive translation, and you're going to see this. Hey, there's an apply statement here, which so I'm gonna have to explain a bit what's happening here. This is not exactly what the intermediate representation is going to be. I just clean it up so that there's not too much like gen simming and things going on. Yeah, so we have the orders table, and we have down here the shipping table. And the supply statement essentially is saying, hey, for every order on the scan, so I'm having order ID here, please bind this to a variable. So whenever you see something with a question mark, it's going to be a variable. And please execute the right-hand side. So, okay, it's an imply semi-join, and please anything from the left side, which is the orders table, bind me x1, which is in this case the order ID, to x1, and then execute the right-hand side. So it's essentially the nested loop that I've described earlier. But then there are some rules that essentially just match against this structure, and that's sort of what I said, where we kind of hook in all the literature that is out there, and we just translate this then to something that is a pure semi-join. And then you don't have this apply in the nested loop anymore. And yeah, so it's like a nice example of where we can kind of hook into the literature and do some optimizations. Coming back to compilers maybe, so what's something that is sort of on a similar magnitude? I would say, for example, loop unrolling. So let's say you have some tiny loop. Normally you would, in your instructions, essentially create that loop, but you can also just say, hey, please create these instructions sequentially, and that is also like a tiny rewrite of your program which optimizes it. So that's sort of doing the circle back to compilers. Yeah, I could go on where we actually use sort of compiler bits and pieces. For example, in the expression engine, we use eval. I've never worked on a project where you use eval sort of in your system. So there you could say it's actually like a whole full compiler that we use to generate stuff. Yeah, so that closes kind of the thing on where they're the same. So I hope I've given you sort of a glimpse on where there's some overlap. So next I'm going to talk about where they're different. For that I grabbed this little diagram from a paper. So on the x-axis, you're seeing the user requirement in terms of simplicity on the left to flexibility on the right. And then the y-axis is kind of talking about the proposed value. Yeah, so let's think a bit about what this actually means on the left side. So we've just said, we've just seen how like our database might work, and then why is it simple? So essentially, like the queries you're writing most of the time are fairly simple compared to a general computation that you might do. So of course, some people might say, okay, but SQL is Turing complete. You can do arbitrary computations. But anything I would say that most of the features that make SQL Turing complete are not actually used most of the time in production. So we write, like when you write an SQL query, you most of the time know, hey, I'm working with finite relations. My SQL query is going to finish at some point, and that sort of is what makes it simple. On the right side, you sort of have then compilers for general purpose languages, which then you could do arbitrary computations with. And yeah, so there's like a divide between the two. So you could probably ask the question, why is there a divide? There's probably historical reasons to that. The two communities have been quite sort of working on things separately. Yeah, so the next thing is I'm going to try to place some projects on this chart. There's some subjectivity to that, but yeah, I hope sort of it enlightens us a bit. So the first thing I wanted to place was site. So Malcolm is going to tell me off afterwards that I've placed this project wrong. So why do I place site there? So I think it does way more than a normal database, but it's still quite like it's a resource server. So it's like you're probably not going to do. Might do some complicated transaction functions, but you're not going to do arbitrary computations inside. So that's where I place site. Yeah, the next thing is ORMs. That's standing for Object Relational Model, which is, I'm actually not sure if it's coming from the Java world, but I'm going to explain it based on the Java world. So you have like a mapping from your objects to the relational world, and like there are these frameworks where you essentially annotate your classes with saying like how the fields are going to be mapped to the database, and like how are the relations to other objects, and then whenever you do like an update to your user, hey, the address changes, the framework takes care of like syncing that to the database. And there's also then the relationships, of course, from the user to maybe his orders. That's like a one-to-many, and you annotate your Java code in that way. So I think ORMs, like, they have their purpose, but they serve, like, as soon as you get into more complicated business questions, they often fail because like the system then doesn't know how to optimize your queries anymore. You do like some very complicated relationship question about your objects, and then these things often fall apart. So this is where I would put ORMs on the slide, because they sit more on the compiler side. But so I guess there you see the subjectivity. I would place site a lot higher than ORMs, but that is of course like subjective. Maybe the other interesting bit about this slide is that maybe they're actually targeting quite similar use cases. So that if you think of CRUD apps, I think Site does that very well, and ORMs also try to do that to some extent. And yeah, so it's like two different approaches to the same problem, but yeah, I think being more on the simple side for that is probably better. Yeah, so the last bit, one other bit I want to place on the diagram is called the language, which is called Morel. I actually didn't put the source below, but it's like an extension of standard ML. Standard ML is like a general purpose functional programming language, strongly typed. And what is nice about Morel is essentially they tried, hey, why do we actually have a difference between like databases and general purpose languages? So if you look at this example, there's like a function from line 1 to 4, and then Morel has this extension to standard ML, which can essentially, it's like quite similar to SQL. So in this case, we getting some employees, and then we check that the department number is equal to some subquery, and we actually use the function just defined above. So the interesting question is, of course, like where do we place where do we place Morel on the diagram just before? And so this is where I would place it, because essentially it's coming from the compiler side, but it's trying to push towards the database side, sort of doing the simple things, but in the same, in the same project. or sorry, in the same system. Yeah, I think it's, some people might also say like, hey, why is it maybe not a good thing that these two things are separated? We have some clear boundary. Let's focus like on the database side on these things, and on the compiler side on these things. And I think it's a valid question. It's just nice sort of to think a bit about it. Yeah, and so the thing I want to close is sort of where would XT sit? What should XT do? So I wrote this little data log program which calculates the shortest path. This actually currently doesn't run because we don't support something. We don't support these aggregates in rules here. But it kind of tries to convey the idea that a user should be able to push like as much logic into XT as they can. And that's also sort of what I want to close with. And on the diagram, essentially, let's try with XT to push from the left side. Stay on the simple side. Let's push to the right, and let users sort of try to put stuff in XT, but don't try to do it sort of like as Morel does, because then you would need to convince people to kind of use a new language. But let's try to push from the left. Yeah, and I hope if you're interested, please follow along and get in touch. Cheers.